All right. Curve of the head versus discharge, and the efficiency versus the drawn discharge are usually drawn. So this is the one actually that we are referring to. We have a head over here, we have a Q over here. Normally we have a head over discharge. Okay, this is the theoretical of the pump. Okay, this is the theoretical, this is the actual condition. Okay, let me have a look first in terms of the data. Curve of head versus discharge and efficiency versus discharge are usually drawn. Okay, let me show it to you, the actual here. We have three different, let we have a look in terms of this diagram first. We have three different graphs actually, there where we can combine as a single graph. We have head over discharge. Okay, this is the typical value. Okay, this is the typical value, even though the formula which is this. Saya tak masuk lagi yang ni ya. Saya cuma nak, let me show it to you a rough idea first before we go in detail. Okay, this is for H over Q. Next, this is the efficiency over Q. Okay, you can see here in terms of efficiency, the efficiency of the pump is doesn't mean you increase the value of Q, efficiency will increase until at a certain Q. That's the maximum efficiency of the pump. If you increase the value of the Q after that, the efficiency will decrease. Okay. In terms of head, okay, in terms of the head, the value of the head will decrease with the increase of the Q. And then the last one, which is power. This is the power input. Okay. This is the power input, where the power input will increase with the increase the value of Q. So we will manipulate all this data in order to get the what we call it just now, the operating head over here. Let's say as simple as that. Okay, I show it to you first, yeah, because I want just to give you some idea. Okay, this is another. Let's say this is the pump in parallel condition. Okay, this is the just now, and then this is the system. Whatever it is, plus one more is in series. Again, the same. Okay, we have a head. This is the one that we are discussed from the beginning. This is the head, single head, pump B, pump A. All right, and then when we combine. Actually, pump in series, we want to increase the value of Q, yeah. We make it pump in series, the value of Q will decrease. And then if we arrange the pump in parallel condition, we will increase the value of head. Okay, so back to the basics. The basic of the equation, again, I said class, this is, we are using the energy equation. All right, nothing new. Okay, the only addition which is the HP just now, head of the, okay, again, now we go for this one first, head and Q. All right, Okay, let me discuss in terms of this one first. Okay, most pump operated in a constant speed. Okay, despite changes in loading. Over here, if we change, okay, most pump operated at the constant speed, meaning that at the motor part, the rotation of the motor, which is constant at one rotation per minute, at one value. Okay, the most common characteristic is to show the characteristic of the pump loading. Curve are called characteristic curve. This one, this is the characteristic curve. All right, so the curve usually drawn for a given design speed. So head versus discharge, it is Q curve. Okay, so this is the formula. The theoretical head is a function of discharge. Okay, this is come out. This value is H is A minus BQ, and then A and B is a constant value depending on the type of pump. So this value of A and B is provided at every single pump, provided from the manufacturer. Yeah. So if we look in terms of the equation, H which is equal to A minus BQ. So this is the actual graph. But what happened for the pump instead of a straight line, there is a curving. Why is a curve? Due to the losses in the pump. Okay. Even though pump will increase the discharge and head, there is a losses also in the pump where the pump is not operate at 100% of efficiency. Okay. So this is common. Even though pump will decrease, giving the added value of the Q and head, but there is also losses, as we discussed in terms of from the previous chapter, what we named it as a separation losses. There is numbers of separation losses which is due to fittings and apparatus. Okay. So have a look back. However, the actual plot of the characteristic curve gives a curve which yield at a value of h less than the given by the theoretical curve. This is what I said before. So this implies that there is a head loss occurring in the pump. All right. The losses due to shock losses as a result of the flow of the water into and out of the impeller. Okay, losses due to the losses at the impeller, incoming and outgoing from the impeller. All right, due to the friction and the turbulence in the pump. So again, so this is the diagram. In the most instant, other characteristic curve is namely a power input. Okay, power discharge. So this is the setup. Okay, this is the setup. All right, for the pump. One, don't forget, whatever it is depend on the system. Okay, it also depend on the system. What is the meaning of the system? Keadaan mana yang kita nak tengok lah. That's why this is the data provided from the pump, but the system is different based from the control sini. This is one of the system from station 1 to station A to station B. All right, at different elevation, and then at different, if we looking on the reality, at a different property. Okay, when talking about head losses, frictional losses is straightforward. What I mean is the separation losses. When we have fittings, okay, we have, let's say we have different numbers of elbow, different numbers of join, different numbers of changes in terms of a diameter. That's the property of the system. So that's why I said that's what this is the meaning that I'm referring to, because the system for system A and system B, which is different. As I said just now, the example that I'm sharing to you is a water treatment plant, a delivery of the drinking water from just now from treatment plant next to the Pahang River to our campus in Bandar Pusat. This might be one of the system for that particular distance. And then other system have different property. Okay. So again, under the efficiency, head actually developed by the pump. Okay, theoretically head minus losses. All right. The head developed. Agree? Yeah? The actual head, which is equal to theoretical head minus losses in the pump. Okay. Efficiency is the ratio of the power output over the power input. So this is the term of the power. Okay. P, which is equal to rho GQH. All right. What is the value of H? And then you get the P in. All right. And then P out. This is the efficiency. Okay. We have a look. Class, we have a look in terms of pumping between reservoir. Okay. Reservoir A at Z1, reservoir B at Z2, and then if we want to convey water from A to B, of course we need a pump at the middle. So this is the arrangement. All right. S meaning the suction, D is the delivery. So what we need to do, again, as I said just now, we need to come up with the energy equation between both points, between both ends. Why? As we commonly practice at inside the tank, the velocity at point A and velocity at point B is reaching zero. Pressure at point A and pressure at point B is atmospheric pressure. So S and D is located in the suction and delivery side of the pump. Pump will increase the head by the difference in terms of elevation, ZB minus ZA. Head difference can be broken down into part HS and HD. Okay, have a look. HS is a vertical distance from point A to a suction part. Okay, and then HD is a distance from a delivery head to point B. So actually, if we have a look mathematically, ZB minus ZA equal to HS plus HD. All right. Thus, ZB minus ZA equal to HS plus HD. And then we bring back to this basic formula. This is the one just now, the first equation that we are discussing. This is the equation. This equation I'm referring to, the same equation. All right. Back to this equation for this example. All right. Okay, back to this equation. What we need to do? Yeah, we just replace this one. Z1, ZB minus ZA or Z2 minus Z1 equal to HS plus HD. Okay. So rearrange back. Okay. We can simply P1 over rho G0, V1 squared over 2G0, P2 over rho G0, V2 squared over 2G is also 0. And then rearrange this. Okay, you will this formula. Okay, so this is the formula. Then you just rearrange as ZP or head of power of pump, which is equal to ZB minus ZA plus H. Okay. So rearrange, this is the head of suction pump, sorry, head of delivery, head of suction plus head loss. All right. We have a example over here. Okay. The diagram, still using this diagram, yeah, but still the same diagram. We have at point A, and then we want to deliver at point B. We want to apply this formula. We want to apply this formula. So it is required to pump water at the rate of 50 liters per second from one reservoir to another reservoir, which has the elevation of 20 meters high. A centrifugal pump is located 7.5 above the lower reservoir. The pipe connecting the reservoir has a 150 mm diameter. All right. The length from the lower reservoir to the pump, which is 100 meters, while the length from the pump to higher reservoir, which is 200 meters. So assuming the friction factor is 0.01 and separation losses are neglected, so what is the head needed by the pump? Okay. Soalan nak head pump tu berapa? Ni. What is the head by the pump? So what we need to do again, as I said, ZB minus ZA, which is equal to HS plus 80. So we notice that from this equation, the difference which is ZA minus ZB, which is equal to 20 meters. So we can HS plus HD, which is 20 meters. Okay. So the head loss in the pipe only due to the friction, since the separation is neglected, and then the diameter is remain constant before and after the pump. All right, when maintained at 0.15. So we have a HF which is equal to FLQ squared over 3.03 d power of 5. You will gain the HF, which is 32.6 meter. So what we gain that the pump head of the pump needed is 52.6 meter for this particular system. Boleh? Okay. Boleh faham tak kelas? The head is needed for this particular pump, which is 50.6 meter. And the capacity, this is not showing the capacity of the pump, ya. Maknanya yang untuk sistem tu perlukan 52.6. Pump mungkin boleh supply 100 meter head. Alright. Yang ni because the way we discuss the issue is based from the system itself. Okay, different system, as I said just now, having the different numbers of properties. Alright. So why we need this? Okay, I need to our class this morning, I will focus until cavitation, because my next video is on the issue also will cover on the cavitation. What is cavitation? Okay, in bahasa which is peronggaan. Right, is we having a bubble. Having a look first in terms of a cavitation, in terms of the theoretical part. Cavitation by theory is a phenomenon in which water in the pump undergoes boiling at a very low temperature. Okay, class, what is the boiling temperature? Our normal boiling temperature What is the value of how many Celsius? How many degree of Celsius?
100.
100 Omar. Setuju? Is it true 100 degree Celsius, Amirul? Lukman Hakim, do you with me?
Yes, 100.
100 meter. Okay, 100 degrees Celsius, right? That's the common value of the boiling temperature in our country. Yeah. What happened at the higher elevation? Have someone traveled to higher country like Peru or Nepal? Ada siapa pernah pergi? At a higher elevation, let's say for 4,000 meters elevation from the mean sea level. Ada siapa pernah pergi? Saya pun tak pernah. But talking about the theory, when we are at the higher elevation, we will facing a lower atmospheric pressure, and then will reflect to reduce the boiling temperature. You can browse from the internet. Let's say at Nepal, what is the boiling temperature? It's about 72, 73 degrees Celsius. The water will already convert from water to gases. Again, what on the cavitation phenomenon, again, this is due to the reduce of pressure. Yeah, phenomenon occurs due to a lower pressure encountered in the pump. As I said just now, we go for higher elevation, the pressure is reduced, and when the pressure is reduced, what happens to the boiling temperature? The boiling temperature is also reduced. So boiling temperature influenced by the pressure experienced by the water, where higher pressure required higher temperature to cause boiling. But what happened in the pump? We will facing the lower pressure. So when the lower pressure happens, the boiling temperature will lower. And then what happened? The water start boiling. Okay. And then will produce a bubble. This is the issue actually in the pump. What we call it, the bubble is the cavitation. The cavitation can be very damaging to pump as it causes the surface of the material coming into contact with bubble to get damaged. I will share with you another video to show this, where the bubble will damage the internal surface of the pipe. Okay, the damage is the result of the bubble forming and breaking repetitively. Okay, so long-term exposure to this issue will cause fatigue, leading to the damage of the surface. All right. So how to make sure this one will not happen? Okay, the formation of bubble will also cause an increase in the specific volume, resulting in choking and lost performance of the pump. So NPSH, which is a net positive suction head, is a measure the susceptibility of the pump to cavitation. Okay, so this is the value where the indication of cavitation. So every single pump will come up with this value. Okay. So kalau balik kepada equation, okay, this is the equation just now when we have a suction at the suction part. Yeah, suction part. It's not on the delivery part, at the suction part. So again, what we have is Zs plus hf. So since the velocity at A is 0, and velocity at A is 0, so and Zs minus Za with Fs, heat of suction, so masukkan balik dalam equation, we will gain this formula. Okay. This formula, the pressure head, this pressure head, alright, this pressure head, Ps over rho g of that particular system must be greater than vapor pressure. Okay, by a certain margin to avoid cavitation. So this one, the difference, we call it as the net pressure suction head. So every single pump will come up with this value. Okay, this is provided by a manufacturer. Okay, pump is one thing, system is another thing. We want to combine the system of the piping system with the additional of the pump, and then the pump the property of the pump which is must fulfill to this. Okay, again, if kita masukkan, kita dapat this formula lah. NPSH, PA over PV, plus VS squared over 2G plus SS plus SF. Okay, so the value and NPSH must be larger as possible. Where the value of 0, alright, if the value of NPSH of 0, meaning that, okay, this zero value of NPSH indicate the cavitation will occur. Okay, so I think I want to cover up to this. The example we will discuss on next class. We will finish this one first before we go for turbine. But the most important part when we talk about your tests and so on, actually the most critical cavitation part is we discuss this on this. This is the critical point. The reality, actually, we are talking about this equation, where with the head arrival from the pump, as I said just now, this curving, every single pump have this property only. Okay, this property for every single pump, and this is the one we want to mesh with our system. As I said just now is from tank A to tank B. Okay, this value, it can be like this, it can be like that, and then we will gain this intersection point. We name it as an operating point in terms of value of Q. Over here, if you drag to X scale, you will gain the value of Q. If you drag to Y scale, we will gain add the value of H. So one thing that I want you to remember is, okay, different system you will gain the different value of heat and Q. Okay, even though we are using the same pump, alright, gunakan pump yang sama pada sistem yang berlainan, tetap kita akan dapat nilai Q dan H yang berlainan. The most important thing in the actual, we want to come up with the operating head and operating Q, because the property of the system is changes among the system. Alright, this is the one yang kita akan tengok next class. Alright, class.